Okay, so binary search trees. These are a special type of binary tree. Not all binary trees are binary search trees, but all binary search trees are binary trees. So now that we know what a binary tree is, we can look at a specific type, a binary search tree. And you're going to find a lot of similarity in the underlying ideas as we saw when we looked at the binary search. So a binary search tree is a binary tree, but all values in the left subtree are less than the value in the root. And all values in the right subtree are greater or equal to the value in the root, assuming duplicates are allowed. We could make the left subtree less than or equal. It doesn't. It's arbitrary. It's just which side do duplicates go to. Typically, you see it on the right-hand side, but it doesn't really matter. Yeah, or we could disallow duplicates or something. So the question I have is, so this is a recursive definition. All values in the left subtree are less than the value of the root node. But the root node, remember, this is a root node, and then 7 is a root node of this subtree. And 3 and 9 are root nodes of their subtrees, and 8 is a root node of their subtree, and so on. So remember that. So in the above two examples, the tree on the left is not a binary search tree because, okay, look, great. 9, well, 8 is less than 9, great. 9 is greater than 7, 3 is less than 7, and 7 is less than 10. So everything on the left checks out. But on the right, we have an issue because 16, sure, is greater than 11, but 16 is in 15's left subtree. And 16 is not less than 15, meaning this isn't a binary search tree. It's close, but it's not. Where over here, this is a binary search tree because everything on the left is less than the 14 and everything on the right is greater than the 14. And that's true for every subtree. Everything on the left of the 8 is less than, everything to the right of 8 is greater than. Everything to the left of the 12 is less than, everything to the right, well, there's nothing. Everything to the left of 26 is less than 26. Everything to the right of 19 is greater than 19, and so on. So there. Okay, in the above example, note that the leftmost node is actually the smallest value, and the rightmost is the largest. So if you start at the root and you go left, 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 left until you can't go left anymore, you found the smallest value in the whole tree. If you're at the root and you go right, 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 right until you can't go right anymore, you're at the largest value in the tree. And if you're saying, well, hold on, how come 15 is the most right and not 12? Well, because you only go right. The rule is only go left to find the smallest, only go right to find the largest. Where if we wanted to get to the 12, we'd have to go right, left, right. That's no good. We only go to the right. And that's just more of an interesting fact. Oh, and look, here is a pull request suggestion. You will notice that I do not have punctuation at the end of any of these points. This one has one. Someone can go get rid of that punctuation for a nice, easy PR. Yep, but it's first come, first serve. Okay, a binary search tree is a binary tree. A binary search tree is a special case of a binary tree. Therefore, it will have all the same properties and operations that our binary trees have, but there's a couple of catches. When we add to a binary search tree, it matters where we add things. Just kind of like with the indexed bag, we could put the things wherever we wanted. With the sorted bag, we couldn't. Whenever we added something to the sorted bag, it had to go to the place that would mean that the sorted bag remained sorted. So it's the same idea here with the binary search tree. If I say add the number, let's say add the number 13. You can't add it anywhere. There is a correct spot to put this, right? And think about how we would find it. Look at the 10. I want to add 13. Should the 13 go to the left or the right of 10? Type it in the chat. This isn't a trick question, and if you're struggling with this, I feel you're in trouble for the exam. Yeah, it goes to the right. Why? Well, 13's bigger than 10. Okay, great. Now we're at the 15. Should the 13 go to the left or right of 15? Let's hear it. Left. Yeah, because 13 is less than 15. Should it go to the left or right of 11? Ooh, right. And should it go to the left or right of 12? Right. If I want to add 13, there is a correct spot. Everywhere else is wrong. Remove, well, okay. So if I come along and I remove the number 8 from this tree, okay, no big deal. The order is still there. But let's say I wanted to remove the number like 15. What do I do? What if I wanted to remove 10? What do I do? How do I address that? Like with the 15, you might say, well, I'll take the left child and put it there or something. But like, what happens if I remove 9? Do you take the left and put it? How do you? Removing's tricky. Remove max, remove min. Well, those are actually kind of easy. Just go to the left, go to the right. But of course, removing the min in this tree, which is go to the left, remove the 3. Okay, you could take that 3 out and the tree's fine. But if you wanted to remove the max, go to the right, go to the right, go to the right, well, we find the 15. If we want to remove it, what do we do? How do we deal with that? Because we can't just get rid of the 15 and then go, well, 11 and 12, you're screwed. No, the 11 and 12 are still in that tree. So we got to put them somewhere. Now, searching a binary search tree. So this is where we're really going to connect the dots with the binary search. The special ordering of a binary search tree lets us search very efficiently. So here is a naive search through a binary tree. Okay, this is the one that we saw. If we go back to the previous topic, at the very end of the previous topic, contains, yeah. So this is what we just saw in the previous topic. Oops. Lab 9. Where am I? I'm all over the place. Go back. 23. Okay. Here is the naive contains. So here's the contains that's not great, but you know, whatever. I'm looking for needle. And I start at the root node. Okay? And so, if the current node is null, it's not there. It's an empty tree. And is the thing we're looking for in an empty tree? No. The answer is no. It's not, because it can't be. Otherwise, if the thing we're looking for is in the node I'm currently looking at, we found it, right? So, okay, either it doesn't exist, and if it doesn't exist, it's false. It exists, and we found it. Great, return true. Otherwise, we do 2 recursive calls. Something like this contains on the or, and another contains. So we do contains, but search the left subtree. So go check the left subtree. Is the left subtree root, does it not exist? Does it exist and we found it? Or do we need to do another search on its left subtree? And so on. So the way this is done is it says, okay, search the left. And if you find it in the left, great. If not, you need to search the right as well. Okay, so either, let's say here, I'm looking for the number, let's say 9. No, let's say like I'm looking for the number 19. Okay, I go 14. Okay, it exists. 14 is not 19, so I'll check the left subtree. Okay, is 8 9? No, check the left. Is 3 19? No. Okay, check the left. Okay, doesn't exist. Check the right. Doesn't exist. Go back. Check the right. Is 12 19? No. Check the left. Is 9 19? No. Check the left. Doesn't exist. Check the right. Doesn't exist. Go back to the 12. Check the right. Doesn't exist. Go back. Go back. Go to the right subtree. Is 26 19? No. Okay, go to the left. Is 19 19? Yeah, it is. Okay, return true. So this is the naive strategy. But because we know the binary tree, if it's a binary tree, it must have the property that anything bigger must be to the right. So we could we could change this search slightly by asking the question, okay, is 14 19? Yes or no? No. Okay. Is 19 bigger or smaller than 14? If it's smaller, I will continue the search only on the left subtree. If it's greater, I'll continue the search only on the right subtree. There's no need for me to look at the left subtree if it's bigger, right? 19 is bigger than 14. I know 19 can't be in the left subtree. So I don't need to look there. So the naive search is linear time. If there's n nodes in the tree, I need to look at all nodes to guarantee if I found it or not. But with a binary search tree, it's not. With a binary search tree, I can get fancy and say, okay, if you don't exist, return false. If the thing you're looking at is what I'm looking for, return true. Otherwise, you compare the elements. If the thing we're looking for is less than what the root node, then search on the left. If it's greater than, search on the right. But before, we're calling two things here. There's two new calls to this recursive function, where here, it's an if-else. There will only ever be one call to binary contains, or binary search. Uh-oh, I think this is... This should be binary contains. I don't know why it's binary search, binary search, binary search, binary. Or maybe this should be called binary search, binary contains, whatever. There's another PR. This should be binary search or binary contains, whatever. Yeah, so here it's an if else. Only one of these recursive functions get called, not both. So that's awesome. So every time we make a decision, we get to eliminate half of the stuff, assuming the tree is reasonably balanced. Did I hear a boop? What should it be? I'd say it should be... Let me go look to see what I called it. No, here. Because it is an important question. What should it be called? Binary search tree. That's the interface. Linked binary search tree. Contain binary. It should be binary search. Contains calls binary search. Yeah. This should be... It should be binary search. The function name. Binary search, not binary contains. Good. It's because you're going to make a PR, aren't you, Bilbo? But that's a good thing. Yeah. Okay. So there we go. For those of you confused at what I was talking about, well, this method here is called binary contains, but I'm pretending it's called binary search here, and in the recursive calls, I'm pretending it's binary search. So yeah, that's a bug in that code. Okay, notice the similarity between the naive search and the binary search. They are nearly the same, except the naive search may end up searching both trees, where the smart one, the binary search, will only ever search the left or right subtree. It will never do both. It can only do one or the other. Yeah, there. So here we go. Let's see. Okay, in the above example, if we search for the number 12, we can conclude that it exists in the tree since 12 is less than 14, so it must be in the left subtree. 12 is greater than 8, so it must be in that subtree's right subtree. And 12 is equal to 12. Therefore, we found it. But if we're searching for 13, we can conclude that it doesn't exist because, okay, is 13 greater or less than? Okay, so it should be to the left. Is 13 greater or less than or greater than 8? Well, it should be to the right. Is 13 less than or greater than 12? Well, it should be to the right. There's nothing there. Therefore, if 13 had existed, it must have been to the right of 12, to the right of 8, and to the left of 14. But because it's not there, we can conclude it's not there. And look, this one has 1, 2, 3, 4, 5, 6, 7, 8 nodes in it. But I only needed to look at 1, 2, 3 and a half, I guess, because that other one's not there. So I looked at 4 things. I got to look at half of them. I didn't need to look at all of them. Where if I was doing an exhaustive search, the naive one, I'd go, okay, are you it? Are you it? Are you it? Are you? I'd have to look at all of them. So there we go. 22 is not there since 22 must be greater than 14. 22 is less than 26. 22 is greater than 19. 22 is less than 23, but 23 has no left subtree, so it can't be there. There's nowhere to keep searching. So we're stuck. Any questions about that? That should be more or less reviewed to the idea behind binary search. But when we talked about binary search, the data wasn't literally stored in a tree structure. We just kind of pretended it was by saying like, okay, you know, we can think of it by splitting things in halves all the way down. Where here with the binary search tree, we actually have the data in a tree structure. So it's even that much more like natural to search it that way. We don't have to think of it as a tree. We've stored it as a tree. So any questions so far? I'll wait a moment to give you a chance to ask if you have any. Okay, well, if you do, throw them in the chat. Okay, add. So like most collection we've seen so far, we want a way to add things, remove things, check if it's empty, get its size. Maybe we probably want an iterator. Those things should be reasonably simple. And we'll want to add, we want the add and remove elements, and this is where the complexity comes in, adding and removing. Specifically, the removing gets quite troubling, or difficult, tedious. Okay, add. Adding to a binary search tree is similar to a binary search. But instead, you just keep going down until you do find an empty spot. And then instead of concluding that the thing isn't there or is there, you just add it. So here's what we're going to do. We're going to do a binary search until there's no child. And assuming we allow duplicates, an element we want to add that are equal to a given node go to the right. So this is assuming that if we allow duplicates and duplicate values go to the right, if we ever find an element that is equal, we continue the search to the right subtree. Okay. Insert the element where the child does not exist. New nodes will be added as a leaf. In English, add would look something like this. If the root of the tree/subtree is empty, insert the new node there with the data that we want to add. If it's not empty, well, if the element is less than the root of that tree/subtree, call add on the left subtree. If it's greater than or equal to, call it on the right subtree. That at this stage, as people who are learning programming, it's probably easier to wrap your head around it with an example. So adding 13 goes like this. Okay, 13, should it go to the left or right of 14? Well, 13 is less than 14, so it goes to the left. 13 is greater than 8, so it goes to the right. 13 is greater than 12, so it goes to the right. There was nothing to the right of 12, and here's the picture up here just to show you there was nothing there. So it goes to the right. So 12, it has a new subtree. It's a single node where its root is 13. So starting with an empty tree, let's add a bunch of things. Okay, we're going to add, what do I have? 6 elements here. I want to add 26, 15, 38, 31, 7, and 34 in that order. Okay, we start with an empty tree and I add 26. Well, okay, 26 is the root. Great. Add 15. Okay, well, 15 is less than 26, so it goes to the left subtree. There's nothing there, so 15 is the root of that left subtree. Add 38. Okay, well, 38 is greater than 26. So it goes to the right of 26. Oh, there's no subtree there. So it becomes the root of that subtree. Add 31. Well, 31 is greater than 26. It's less than 38, so it must go to the left. We add it there. Add 7, left, left. Add 34, right, left, right. As you can see, it's the same as a binary search, except the binary search tells us if something is there or not. Instead, we're doing a binary search to find where it would go, and then we add it there. That's the difference. The algorithm is effectively the same, just tiny little difference. Okay, min and remove min and max. Could you do an example like this in IntelliJ? I believe that is the next topic. And didn't you notice that we looked at the linked binary search tree? See, let's see. See, here's your ad. See, it's the same as the binary search. But we'll cover the specifics of the algorithm in Java in the next topic. Yeah. The leftmost, okay. Min and remove min. Okay. Given the nature of a binary search tree ordering, the node with the minimum element must be the leftmost node in the tree. There are 3 cases we'll have to take care of when looking for the minimum node. The leftmost node is the root, meaning the root has no left child. The leftmost is a leaf node, it has no children, and the leftmost node is an interior node. So, the 3 cases, do I have a picture? Okay, cool. I do have an example, good. So finding the minimum is simple. Assuming a root node exists, keep going to the left subtree and there's no more left subtrees. Right? So finding the minimum is simple. You're at a tree, go to the left, go to the left, go to the left until you can't anymore. And then whatever is there is the minimum. And let's look at the real quick here. Remove, file replacement, remove min. I just want min. Okay. Okay, here's the min. It's a recursive one. It takes a current node. If currents left is equal to null, meaning there's no more left nodes, well then give me currents data. That's the minimum. Otherwise, do a recursive call on the currents left if it exists. So this is go to left, go to left, go to left, go to left until the node doesn't have a left anymore, and then it must be there. And here's similarly with max. It's the exact same except go to the right. So remove will be a little trickier. So finding the min and finding the max is easy. It's very simple. But removing it can be difficult because they might have children. And further, not only must the children stay in the tree, but the proper binary search tree ordering property must be preserved. So like I can't just take 15 out and then replace it. Maybe we'll see an example in the example. All right, consider the following examples and think about how one would manage potential children of the node being removed. So here's the initial tree. I want to remove the minimum. So I go to the left, go to the left. The minimum's the 7. Great, so I take out the 7. But now I've got this dangling 9. Where do I put it? Well, in this particular case, it's not too bad. I guess I can just put 9 and be like, well, okay, look. Because 9 is in 15's left subtree, I know 9 is less than 15, right? Anything to the left of 15 must be less than 15. So I can take this lonely little dangling 9 and kind of like promote it and have it take the 7th spot. And this still preserves the binary tree ordering. Now, if I remove the minimum again, well, this one's the really easy case. It's the 9. So I go to the left, go to the left. Oh, it's 9. Great. I remove the 9. I just take the 9 out. And now it's fine, right? Because, well, there is no, like, there were no children to deal with. There was no dangling children that I needed to take care of. If I do it again, though, I'll have to remove the 15. So we go over here. We got the 15. Okay, so we remove the 15. Now we've got this dangling 18. Well, we can do the same thing we just did with the 9. Kind of promote that 18 to be 26's left child instead of 15 because we wanted to remove the 15. Yes. So great. Remove the minimum again. Okay, this one, it's a leaf node. Remove the minimum. Cool. What was it was 18. So we just removed the 18. 18 has no children. It's fine. So this is the shape of the tree, which doesn't really look like a particularly good binary tree anymore, considering 26 has no left children, but it still is. Remove the minimum. Well, this is now the case where the minimum's the root. And here, it's actually not too bad again. We just remove the 26, but then we make, the right subtree become the root of the whole tree, right? So 26's right child becomes the whole tree's root now, right? So, because if we remove 26, we've got the dangling right subtree that we need to take care of. Well, it's just promoted to be the whole tree. So what do we say here? Case 1, the minimum value is in the root node. This means that there is no left subtree. There may be a right subtree. Therefore, we simply make the root of the right subtree, which might be null, the new root of the whole tree. That's what happened here. We want to remove 26, simply take the right subtree and make it be like the root of the whole tree. That's what we did. Imagine 26 didn't have a right subtree. 26 was just a lone node. It's a binary tree node, a binary search tree node with the value 26 in there. And if I removed it and I replace the root node with 26's right, which pretend it doesn't exist, so it's null, well then it's fine, because if I just remove the minimum and the root node had no right subtree, it's got to be empty then. Okay. The ordering is preserved since nothing is in the left of the root, so there's nothing less than. Everything to the right of the root is larger than the value in the root, or equal to. The right subtree is a binary search tree by definition. Therefore, if the right subtree becomes the new root, the binary, or I guess really I should be saying if the right child becomes the new root, the binary search tree's order will be maintained. Any questions about that? If you do, throw it in the chat. The case 2, well, this is if the minimum's a leaf node. This means that 1, we have no children to deal with, therefore just remove the node. By eliminating only a leaf node, the ordering will not be affected. Did I hear a boop? No. Right? If I remove 33, it's fine. Nothing is being thrown off. There's no dangling children left to be addressed. And then case 3, we're removing an interior node. This means that, and if it hasn't been clear, these are like logical statements that are facts. And if you don't trust me, just slow down and think of these a little later. Think on them a little later, and you'll be able to convince yourself that these are like matters of fact. So we're removing an interior node. This means that the node has no left subtree. Because if it did have a left subtree, then it wouldn't be the minimum, because anything in the left, if it exists, must be smaller, right? So the node has no left subtree. That must be the case if we are looking at the minimum that is being removed. Example here would be the 7. If 7 is the minimum value in this tree, 7 cannot have a left subtree, because if it did, it wouldn't be the smallest. It would be like me saying, oh, 15. 15 is the smallest value. Oh, but 15 has a value to the left. That's 9, because 9 is less than 15. Well, then 15 could not have possibly have been the smallest value. Right? Thumbs up if you understand, because, or raise your hand if you understand, because your quietness is, all right. I'm seeing a lot of hands, so I'll assume you speak for everybody. If you don't understand, though, you got to ask questions. That's on you. Okay, case 3. Okay. A right subtree exists. Well, why does it exist? Well, because it's an internal node. It's this case that means we're removing an interior node. If it didn't have a right subtree, it would be a leaf node. Therefore, remove the node and make the node's right subtree's root replace it. The node being removed's parent's left child will become the node being removed's right child. So that's saying here the node being removed's parent's left child will become the node being removed's right child. That's a lot of relative terms there, but 7's parent, 15, 15's new left child will be 7's right child, right? So it gets promoted. And if it wasn't obvious when we remove the maximum, not the minimum, it's going to be the same, just in reverse. Okay, case 3. The ordering is preserved in the same way as case 1. Nothing is to the left of the node. Everything to the right of the node to be removed is larger than the value in that node. The right subtree is a binary search tree. Therefore, if the right subtree replaces the node being removed, the binary tree's order will be maintained. All the cases are the same. You may have noticed that the rules for each case are actually identical. Replace the node with the right subtree. So I just spent all this time talking about, well, there's 3 different cases. But the algorithm we use to implement these 3 different cases are actually, it's just one algorithm. The rule is, replace the node with the right subtree. This is obviously more obvious in case 1 and 3, right? If I'm removing the root, replace that node with its right subtree, right? The 26, well, 38 becomes the new thing. If I'm removing 15, or let's say 7, replace the 7 with its right subtree. But when you're removing a leaf node, remember, a leaf node has a left and right subtree, but they're just null. They don't exist. They exist, but they don't, right? So replace the 9 with its right subtree, which is null. Meaning 15's left subtree gets replaced with null, which is fantastic. If you have a thing where it's like, oh, I have all these 3 peculiar little cases, and then you realize that the algorithm to address all 3 cases is exactly the same because all the 3 cases are technically kind of identical, that's fantastic. Yeah. Any questions about any of that? If you do, throw it in the chat. Remove max, it's exactly the same as remove min, except instead of going to the left, you go to the right. Instead of replacing the node with its right subtree, you replace it with its left subtree. So let's go have a look at remove min. So this is the recursive one, remove min. So here's the public one. Okay, if left child's left is null, current, set your left to left's right. Okay, so this method here takes a current and a left child. So in the case of removing the 7, okay, current will actually be 15 and left child will be 7. So we are looking at this recursive method, and we are at the state where 15 is current and 7 is the left child. So it says, hey, left child, is your get left null? Yes, because left child, your left is null. This is just saying, okay, we found the minimum. If it's null, the current, 15, the left, your left is now going to be the left child's right. So current, 15, your left is going to be the left child, 7's right, which is 9. So it's exactly what we were talking about. Then return left child's data. Great. If we didn't find it yet, just recursively keep going down until you find it. That's all. Cool. There we go. So remove min. So now general remove. This is where things, if you were angry a moment ago about that being complicated, I got some bad news. This is where things get more complex. I don't want to say they're hard. I don't want to say they're difficult, and I definitely wouldn't say they're complicated. Even though I just did, I misspoke. They're complex. There's a difference. Wait, but when you return left child data, won't it return left child's get right? No, because current, remember, left child here is, let me draw it. I'll do it with the mouse. Okay, you get it, but you know what? I'm going to draw it out anyways because I wouldn't be surprised if other people are having a similar situation. So here's the 15. Here's the 7. And here's the 9. Right? Yeah. So, and I'm also going to say this is current C. And this is left. Okay. So, in the code, I say current set left to left's right child. So I say, okay, current, your left is now left's right child. So you go like this. Okay. Then I say return left child get data. Well, left still references the 7. We still have access to that 7. So that's why we're good. Yeah. So there you go. Isolation is cheeks. Don't save. Cool. That was a good question. I'm glad you asked. So general remove is where things get complex because it's intricate. So in the above example, there may not be an immediate, obvious, or clear way to address the problem. If I say remove 26, what do? I'll wait a second and have you look at this and so you can think. Wait, what do I do? Do you replace it with the 15? I mean, that will kind of work. Do you replace it with the 38? Well, replacing with the 38's trouble because the 31 should be to the left. I don't know. Case 1, if the node we are trying to remove is a leaf node, then simply remove it. So if I wanted to remove 7 or 34, that would be easy. Remember, this is a general remove. This isn't remove min, remove max. This is a remove some arbitrary value that I specify. So if I remove 7, that's easy. You just get rid of it. Remove 34, just ditch it. Okay, we're fine. Leaf nodes are easy. If the node we are trying to remove is an interior node, this is where things get hairy. In some cases, it might be simple. In the case of remove 15, just replace it with its child. If I replace the 15, if I want to remove 15, it's easy. Replace it with its child. Okay? But what happens if we try to remove 26? Well, how do we do that? Well, fortunately, there's actually a very simple trick. The simple trick is intuitive, but it can get a little hairy to implement, but we'll look at an implementation. I guess we'll probably hit that tomorrow. But the trick is replace the node with its in order predecessor or successor. In this case, I think we want to do predecessor. Okay, so if we remove 26, we could replace it with 15, the value in the tree that comes right before 26. Remember, in order. And in order is left, current node, right. So the in order traversal of this tree is, okay, 7, 15, nothing to the right, finish the left, 26, go to the right, go to the left, go to the left, print it, nothing there. Print out 31, go to the right, print out 34, return, print out 38. So the in order of this binary search tree is 7, 15, 26, 31, 34, 38. As an interesting note, if you have a binary search tree, the in order will always be the numbers in their correct order, just as an interesting anecdote. Let's go have a look real quick at this one. In order is 7, 9, 15, 18, 26, 33, 38, 59. Those numbers are all like increasing. So if you're wondering, oh, how am I going to do this? And you somehow magically forget what the in order rule is, even though, you know, pre, in, post should be fairly obvious. If you ever forget, just look at the numbers and be like, okay, what number in this tree comes before 26? Well, it's the 15. What number in this tree comes right after the 26? Well, 38 is after, but 31 is the smallest number that's bigger than 26. 15 is the biggest number that's smaller than 26. The easiest thing to do is, hopefully this was obvious. If not, it's fine. But if I'm looking for the biggest number less than 26, well, that would be 26's left tree's rightmost value. Because this tree right here's maximum is the thing you get by going to the right, going to the right, going to the right, going to the right until you can't anymore. To find the number that comes right after 26, which would be the smallest number in 26's right subtree, is we'll find the minimum of the right subtree. So go to 26's right and then go to the left, go to the left, go to the left, go to the left until you can't anymore. Which is pretty cool, right? So, okay, the trick is if we remove 26, we replace with 15 the value in the tree that comes right before 26, or 31 the value that comes right after 26. The reason this will work is if I'm looking for the predecessor, so the 15, all values in the left subtree are smaller than the root and everything to the right. The value in the left subtree will be greater than or equal to all values in the left subtree. Yes. The largest value in the left subtree will be less than all values in the right subtree. Wait, is this one correct? The largest value in the left subtree will be greater than or equal to all other values in the left subtree. Right. So, yeah, the largest value in the left subtree will be greater than or equal to all the numbers in the left subtree. Yeah. Therefore, okay, that was that one. The largest value in the left subtree will be less than all values in the right subtree because they're in the left subtree. Therefore, the largest value in the left subtree can replace 26 without destroying the ordering since it's greater than or equal to everything in the left subtree and smaller than everything in the right subtree. And you can do the exact same thing if you made the argument for replacing it with 31 instead of 15. All values in the right subtree are bigger than the root and everything in the left subtree. The largest or the smallest value in the right subtree will be less than or equal to all other values in the right subtree. The smallest value in the right subtree will be greater than all values in the left subtree. Therefore, the smallest value in the right subtree can replace 26 without destroying the ordering. Blah, 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 blah. Again, these are all logical matters of fact that if my explanation right now didn't satisfy you, if you take the time to think about this on your own, piece of paper and a pencil, you can convince yourself, I'm certain. If you made it this far in the course, you can. So below is the example of removing multiple elements from a binary search tree. So here's the initial tree. If I want to remove 70, this is the 70. Fortunately, 70 is a leaf, so it's easy. You just ditch it. Next, remove 7. Okay, here's the 7. We've got an issue. 7 is an interior node. So we can replace it with, it looks like here, I'm going to want to replace it with the smallest value in its right subtree. That's just 9. So 9. Now if I want to remove 38, here's the 38. Now we're in trouble. Okay, because, well, I've got to, what do I do? Well, here I'm replacing it. I mean, I can see it's 36. And 36 is the biggest number in 38's left subtree. Why? Well, go to the left of 38. That's the left subtree. Then go to the right, go to the right, go to the right, go to, until we hit the 36, until we can't go to the right anymore, and then we're done. Take the 36, put it where the 38 was. Boom, we're good to go. Because notice, 31 is less than 36. 34 is less than 36, and 33 is less than 36. Oh, and 36 is less than 59. And we know this because, well, 36 was to the right of everything in the left subtree, meaning it must be bigger than or equal to everything else in that subtree. Equal to if we allow duplicates, right? Because imagine I had another 36 in here. Well, 36 would go to the right. And because 36 existed in the left subtree, because 36 is to the left of 38, I know it must be less than everything to the right of 38, the 59. Removed, I heard boops. What happens if there are duplicates? Do they move? You only need to remove one. Keep going, just find the biggest. So go to the right until you can't anymore. Oh, wait, I guess if we always wanted duplicates going, if you always want duplicates going to the right, you would replace it with the smallest element in the right subtree. If you wanted to have duplicates go to the left, you would replace things with the biggest number in the left subtree. So the way I'm doing it here, duplicates should actually be going to the left, FYI. But those are specific edge cases that don't matter right now. Remove the 26. Well, the biggest number in the left subtree, that's the 15. Remove 31. The smallest number in the right subtree, well, that's the 33. Okay, and I guess we'll have to stop here. We're out of time. But contains, that's just a binary search. Count the number of a given element, that's just a binary search where you also have a count. So here's where we'll pick up tomorrow. Balance versus degenerate. We're basically done, but yeah. Any last questions before we wrap up today? All right, I'm gonna stop the recording.